So good evening all of you. Is the audio and video clear to everyone? Thank you. So let us begin our today's session. So as per the discussion made on the previous class with regard to continuity, do you have any queries? The concepts what you have learned so far? Right? Then the objective of today's session will be, so I want to take one or two problems on continuity. Then I want to discuss some properties of continuous functions. Later, the concept of sequence criterion, and the last part is uniform continuity. So these things I want to focus on today's session. Fine. So please take a note of them. After noting, you please tell. Right. So let us take a problem that you take the function f of x equal to mod x plus mod x minus 1. So we are going to discuss the continuity of the function at the points 0 and 1. That is the claim. So is the function continuous at the points 0 and 1? That we need to discuss. Fine. Now here what happens, earlier whatever the problem you consider, initially you have the bifurcation of the function. So between 0 to 1, 1 to 2, 2 to 3, how the function looks like. That is actually given in general for every problem. But it is different here. The function is given that f of x equal to mod x plus mod x minus 1. So what happens? You need to bifurcate the function values with regard to the objective of your problem. So what we are doing, you are going to calculate what will be f of x when x is less than 0, x equal to 0, x equal to 1, x is greater than 1, x is lying between 0 and 1. So that if you bifurcate the function values in this manner, then it is convenient for you to calculate the limit portion, hence you can verify the continuity of the function. Fine. Is that clear to all? Right. So first of all, if x equal to 0, then what will be f of x? In other words, you are calculating f of 0. Say, what could be the value? If you substitute 0 in place of x, the value will be 1, isn't it? Right. So if x equal to 1, then what happens? You are calculating f of 1 value. What will be the value? 1. Now take the case that if x is greater than 1, so just assume that x is 2, 3, 4, any number. Then mod x is nothing but x and mod x minus 1 is nothing but x minus 1. Since f of x is sum of these two values, you are adding them, it will be 2x minus 1. Accepted? how we are calculating the mod value? Any queries to anyone? Please tell. Fine. Suppose if x is less than 0, say 0.5, minus 0.5, minus 0.3, etc., etc. In such case, mod x will be minus x, modulus of x minus 1 will be minus of x minus 1, and if you sum up the values, it will be 1 minus 2x. Accepted? I think you know how the mod will be defined. We defined mod x in such a way that minus x if x is less than 0 and x if x is greater than or equal to 0. I think this definition is known to everyone. Am I correct? If not, you please take a note of it. So, after this, one more case is left, that if what happens if x is less than 1 and greater than 0. So, you are taking a number which is lying between 0 and 1. In such case, mod x will be minus x. Sorry, mod x will be x and mod x minus 1 will be minus of x minus 1. So, it will be 1 on summing up. Is that clear to all? So, this is for your rough work. You are going to do this calculation on a rough part, and while writing on paper, we say that the functional values of f will be classified as, or we will write the functional values of f as f of x equals to 1 minus 2x if x is less than 0, 1, 0 less than or equal to x less than or equal to 1, 2x minus 1 if x is greater than 1. So after consolidating the results what we have done so far, this is our final output. Will you agree? So based on this, you are going to calculate the limit portions. Since you need to verify the continuity of the function at the 2 points 0 and 1, we are going to calculate that. So continuity at 0. So from this allocation you have f of 0 is equal to 1. You calculate limit extends to 0 minus f of x. From this it is limit extends to 0 minus, the value will be 1 minus 2x, the value will be 1 after applying limit. So if you calculate the right hand limit, limit extends to 0 plus f of x, it will be limit extends to 0 plus 1, the value will be 1. You can observe that left hand limit, right hand limit and functional value, all the three values are equal. Do you accept? Right. Similarly, you can check the continuity of f at x equal to 1. So you can calculate the left limit, right limit as well as functional value. So can you do this on your own? All of you? And tell me whether it is continuous or not. Any questions for anyone so far over this model? Fine. So is this continuous? So let us wait for the others too, whether they have done it or not. So the underlying idea here is, whenever the function is defined in such a way, then you are going to bifurcate the function values as per the limit needs. At what point you are checking the continuity of the function, so that you are going to bifurcate the function with respect to that point, less than, greater than, and equal to. Hence you can evaluate the limit condition. That is the whole idea behind this. So can I take the other problem? Please take a note of that. Fine. So the other thing is, this is the thing, find the points of discontinuity for f of x defined by So this is the thing mentioned. Please take a note of this. Then we will discuss. So I say that you take the interval as closed interval 0, 1. Yes. So in this problem, you are going to find the points of discontinuity for the function f of x on this closed interval 0, 1, where f of x is defined like that. So first of all, let us evaluate the values that what will be f of x as per the definition considered. Suppose if you take that n is equal to 0 in this expression, then what happens? 1 by 2 is less than x, it is less than or equal to 1. And how the function is defined? 1 by 2 power n. In other words, whenever you have this kind of expression, the upper value you are taking it as function value. So here the upper value is 1, so f of x value is 1. Accepted? Let us do the other one. If you take n is equal to 1, so from this expression 1 by 2 square is less than x less than or equal to 1 by 2. So here the upper bound is 1 by 2, so the function value is 1 by 2. Is it clear how the function is defined? All of you? So if you compute the next one, f of x is equal to 1 by 2 square, whenever 1 by 2 cube is less than, x is less than or equal to 1 by 2 square. So the function value is nothing but the corresponding upper bound here. As and when you choose x between these two values within the interval 0 and 1. Now this is the bifurcation of the function. In this way you are going to continue. Now you are going to verify the points of discontinuity. So since the first bifurcation is done at the point 1 by 2, so let us calculate limit extends to 1 by 2 minus and limit extends to 1 by 2 plus. That is our calculating. So if you take limit extends to 1 by 2 minus, this is the thing you need to consider, isn't it? So the function value will be 1 by 2. Accepted or not? So if you take limit extends to 1 by 2 plus, this thing you are considering, so the value will be 1. This is the left limit and this is the right limit taken from these two. In other words, in a short note you can write like this, that if we are checking the continuity of the function at the point 1 by 2, so here it is taken like this. So between 1 by 2 square to 1 by 2, the function value is nothing but 1 by 2. So from 1 by 2 to 1 by up to 1, the function value is 1. The right neighborhood as well as left neighborhood if you consider. So from this, left limit value will be 1 by 2 and right limit value will be 1. Fine. So in this manner, if you are going to calculate at every bifurcation, you can observe one common thing, that whenever you consider the neighborhood in this manner 1 by 2 power n, if you go on to consider the left neighborhood as well as right neighborhood, the right neighborhood will be 1 by 2 power n minus 1. The left neighborhood will be 1 by 2 power n plus 1. So if you calculate the left limit, it is nothing but 1 by 2 power n plus 1. If you calculate the right limit, it will be 1 by 2 power n minus 1. For n is equal to 0, 1, 2, 3, so on. So this gives the left limit value and this gives the right limit value. Am I saying correct? I can say in this way, since you are taking the upper bound as the limit, 1 by 2 power n, the upper bound in this part the upper bound is 1 by 2 power n minus 1. So the left limit will be given as 1 by 2 power n and right limit will be given as 1 by 2 power n minus 1. Always the values are unequal. So we can say that the function is discontinuous at these points 1 by 2 power n, where you can take n is equal to 0, n is equal to 1, 2, 3, so on. You are excluding at the point 1. Is it clear? So whenever you take a neighborhood, left neighborhood and right neighborhood, you are taking the upper value. Say, yes or no? Yeah, I will repeat this again. Just hold on a moment. I will draw this again. Suppose you are checking at the point 1 by 2, the limit portion. So you are calculating the left limit as well as right limit. So whenever you consider a neighborhood, you should take the left neighborhood as well as right neighborhood, isn't it? Yes or no? So here it is going to take like this 1 by 2 square and this is 1. How I am taking this type of bifurcation? Observing the first two equations. 1 by 2 less than x less than or equal to 1. 1 by 2 square less than x less than or equal to 1 by 2. So this portion is giving the left neighborhood. This portion is giving the right neighborhood. Isn't it? Is that clear from the first two inequalities? Fine. So if you observe the inequalities, how the function value is defined? Whenever you have an inequality, the upper value is taken as the function value. So if you choose x here, the upper value is 1, so the function value is 1. So if you choose x in this portion, between these two, the upper value is 1 by 2. So this is the value of the function. Fine. So if you calculate limit x tends to 1 by 2 minus the function value, its value will be 1 by 2. If you calculate the right limit, limit x tends to 1 by 2 plus f of x, its value will be 1 for the neighborhood and for the neighborhood. Agreed? Is it giving an idea or not? So if you generalize the category that if you have a neighborhood in this model, you are checking the discontinuity at the point 1 by 2 power n. N will be 1, 2, 3, so on. If you take n is equal to 1, you are checking the discontinuity at 1 by 2. If you take n is equal to 2, you are checking the discontinuity at 1 by 2 square, etc., etc. So if you consider the right neighborhood, left neighborhood as well, here 1 by 2 power n minus 1 will come, 1 by 2 power n plus 1 will come. So in this left neighborhood, the upper part is 1 by 2 power n. So if you calculate the left limit, this number gives the left limit. So in this right limit portion, if you calculate the function value, this is the upper bound. So this gives the right limit value. Both numbers are unequal. On closed interval, it's continuous on 0 and 1 means the function must be defined right. So if you take 0, at 1, if you just check left continuity, it is okay. At the point 1, it is continuous. At 0 also it is continuous. You are checking the only discontinuous points, not the continuous points here. Because as per the bifurcation is considered, between the interval bound what you have specified, it is always continuous. As and when there is a bifurcation, at the bifurcation point only it is becoming discontinuous. So how many such points are there? You are actually counting there. Right. Fine. So in this way, the points of discontinuity are given by 1 by 2 power n. So can you take 0 here? N is equal to 0. That means, is it a point of discontinuity? At x equal to 1. So excluding the end points, it is going to be discontinuous in the middle points you can take. So all of you agree or any counterpart you have? Please tell. So is the logic clear in bifurcating the function and calculating the limits? All of you. Any more queries, please? Yeah. So here the points of discontinuity are nothing but x is equal to 1 by 2 power n. Where you specify the numbers, what are they specified? 1, 2, 3, so on. So here the conclusion is nothing but f is discontinuous at x is equal to 1, 1 by 2 power n, where n is equal to 1, 2, 3, so on. This is the conclusion. Because if you take n is equal to 0, you are going to check the discontinuity at the point 1, which we don't discuss. Because you are just going to calculate only one thing, the bound existed like this. So 1 by 2 square 1 by 2 cube, so on. You are checking the points of discontinuity like this. And at here, there is no need to check, because the function is defined as 1, which is a constant function, so it is continuous. There is no variation in that. Okay? So 1 by 2, 1 by 2 square, 1 by 2 cube, so on. These are the points of discontinuity. Clear? Fine. So after this, I just want to give some of the properties. Then I go with the sequence criteria. They will be useful to you. As you know, the properties of limits, the similar properties will be obeyed by the continuous functions. In other words, the algebraic properties of limits, if you particularly call. So, if you take two functions, f and g, f is a continuous function, g is a continuous function, defined on the same interval, then f plus g is also continuous. So we have the algebra properties for addition, subtraction, multiplication, division, isn't it? So similar properties will be satisfied by the continuous functions. The same thing we have discussed while going for the algebraic properties of the limits. So here it means that since continuity will be defined point by point, the actual meaning here is if f is continuous at a, g is continuous at a, then f plus g is also continuous at a. That is the actual meaning here. And how do we define the f plus g? F of x plus g of x. So if you call the difference of functions f minus g, f of x minus g of x. Is that clear? The property. So if you take the product of the functions f and g, f g of x will be defined as f of x into g of x. It will be continuous. And we go for the division. If you consider f by g, where the denominator is not equal to 0, then it is also continuous. And one more property, if f is a continuous function, whenever you multiply with this a number, say cf, it is also continuous. If I say f is a continuous function, then I can say 3f is also a continuous function. Like that. If f is continuous, then minus 1 into f is also a continuous function. Is that clear to all? The algebraic properties. So, why should we learn these algebraic properties means, these have some advantage. Whenever you have a function defined as a sum or addition of two more functions, then this type of thing will be useful in deciding its continuous nature. I just want to give one example. I don't want to go in deep of it. Suppose you have a function given like this. F of x is equal to modulus of x plus x by 1 plus e power 1 by x for x not equal to 0 and 0 for x equal to 0. Let us say the function is defined like this. Now, if it is asked, discuss or verify whether the function is continuous or not, say at the point 0. Right? So, we are going to verify the function is continuous at 0 or not, if the question is asked to you. So, apart from calculating the left limit for the whole thing and right limit for the whole thing, you can feel that this function is nothing but sum of the two things. One part is modulus of x, another part is x by 1 plus e power 1 by x. So you feel that this is one function g or g1, another function g2. So if you individually verify that g1 is continuous at 0, g2 is continuous at 0, then addition of continuous function is continuous, g1 plus g2 is continuous at 0, nothing but the function f is continuous at 0. That is the underlying idea. Okay. So whenever the given function looks like a complex one, but it can be written as sum and addition of the values, the functions I mean, then by verifying the continuous nature at the point individually for each function, by combining the result, you are going to verify the given function is continuous or not at that particular point. That was the underlying idea. Okay. So here the result is it is continuous at 0 that you take, because mod x is continuous at 0 and that function is continuous at 0. So obviously the function f is continuous at 0. Any more queries you have to ask here at this concept? To anyone? Please tell. So can I take the other property? Is my voice clearly audible to all? Or am I going speed? Is this comfortable for you? The conversation? Thank you. So one interesting nature here is if f is continuous function, then if you consider modulus of f, it is continuous. It is a result. Let us prove it. I think it is asked in one of the previous year questions. I hope so. If f is continuous function, then mod f is continuous function, right? Let us prove that. You suppose this. The function f, whatever you have taken, is a continuous function. Now, we are going to prove mod f is continuous. We use the definition part as it is. Since f is continuous, first of all, let us write the definition first. For epsilon greater than 0, there exists delta greater than 0, such that whenever mod x minus a is less than delta, implies modulus of f of x minus f of a is less than epsilon. So what I am saying, if f is continuous at a, f from s to r is a function, you take that a belongs to s, continuity will be defined by point. The problem with real analysis is always we should go theoretical. You cannot go graphically, because there are some functions which are piecewise continuous. The simple example is earlier you have done a problem that sorry, f of x is equal to this problem you have done, and you observe that these are the points of discontinuity for this function. Now my question is, if I say integral 0 to 1 by 2 power n dx, can you calculate or not? Is it possible to calculate or not? Integral 0 to 1 by 2 power n dx. All of you, please tell. No, is it not possible? If it is of the form 1 by 2 power x, we are getting confused, then is it possible? Okay, we will discuss that part later. Let me say, so can we do integral tan x? Right. Now, is tan x is a continuous function or a discontinuous function? If you take an interval, say integral 0 to 2 pi. Now, the question is, can we say that tan x is a discontinuous function for infinitely many points? For infinitely many points, tan x is discontinuous. So in this interval, for finitely many points, it is discontinuous. Agreed? Right. So if I erase this interval, it is discontinuous for infinitely many points. Will you agree? Yes. So what happens, even though the function is discontinuous for so many values, it is integrable. Here also such type of situation will arise. Why I am choosing this conversation? Because the concept of continuity is related to integrability. So while doing integration, we will learn a concept that if the function is continuous, then it is integrable. You are going to find its integration value. So if f is continuous, then f will be integrable. So if I am saying that if f is continuous, mod f is continuous, means mod f is also integrable. So if you say that I am showing that if f is continuous by means of a graph, mod f is continuous, you should say that by the same graphical approach, since f is integrable, mod f is also integrable. Is that conversation somewhat sustainable in proving graphically? Are you getting my point? So if you say that by assuming f is continuous, graphically I will prove that mod f is continuous. Since continuity is a related concept to integrability, every continuous function is integrable. So if f is integrable, by assuming that, you are going to prove that mod f is integrable by means of a graph. So how we are doing that? Because the function is not known to you. So what kind of graph you are going to draw? It may be of any type, any curve, a straight line, or any fixed region you can take. So the problem with analysis is we always go more theoretically, but the questions will be asked problematically. We will solve the problems. Theorems will not be given to you. That's why I have chosen this example. Thank you. So where are we? I have taken a function. The domain is S. I took a point A. Since the function is continuous, at every point it is continuous. So f is continuous at A. So by assuming this property, I am going to prove that mod f is continuous. That is my task. So since f is continuous at A, I have written the definition. For epsilon greater than 0, there exists delta greater than 0 such that whenever mod x minus a less than delta, implies this value is less than epsilon. Here we need to understand that whenever you choose a point x in the set S such that x is in the neighborhood of A, in other words, you can choose x within this range. So such that the difference between the distance between A and x is less than delta, then the difference between images is less than epsilon. This is the actual meaning of continuity. Okay? Is that clear? Fine. Now we are going to prove that mod f is continuous means we should prove the same thing here. What we need to prove for epsilon greater than 0? Yes, every continuous function is integrable. For epsilon greater than 0, there exists delta greater than 0 such that mod x minus a less than delta implies modulus of this thing you need to prove. Clear? Right. So step function is integrable. So each step function is a continuous function? No. At every integer values it has a discontinuity, right? Because if you draw the graph of step function, it is going to come like this. It has a jump discontinuity. So whatever the real number you take, from 0 to 1 its value will be 0. So from 1 to 2 its value will be 1. From 2 to 3 its value will be 2, like that it is going to come. The step function, if you draw the graph, it has many points of discontinuity, but it is integrable. You will find that value. That's why theoretical results are useful in solving some practical problems. So this is my task. I should prove that this is going to happen. So consider the value. So in the function mod f, I am taking mod f at x, mod f at a. I am considering. Please understand, x is taken in the neighborhood of a. By assuming that I am taking this value, I need to prove that this is less than epsilon. This is equal to modulus. How the modulus of a function defined? It is defined as, for the image, you are taking the positive thing. So this is mod f of x. This is mod f of a. Are you getting the idea? The difference between these two? Right. And one small result, you know that whenever you take this type of thing, all of you agree for this result? Right. So you feel that here a and b are nothing but real numbers. So if you are applying modulus of f, if you are calculating modulus of f of x, means it is a real number. It is a real number. So this is less than or equal to modulus of f of x minus f of a. Right. And as per our assumption, this is less than epsilon. Therefore, whenever you choose x in the neighborhood of a, if you consider this value, it is becoming less than epsilon. Therefore, mod f is continuous at a. That is the solution. So the solution is just 3 lines, not a big proof. Just 3 lines. The proof is, what I have done so far, I took a continuous function, I took a point. Since f is continuous at a, I have written the definition. To prove that mod f is continuous, I have considered the part and I proved that this is less than epsilon. Therefore, by definition, mod f is continuous at a. It proves our claim. Okay. Yeah. This part you are asking, right? This one. Yeah. If f of x is equal to minus x square, tell me what is mod f of x? Is it x square or not? Right. How do you tell that it is x square? So the difference here is, while defining mod f, I am defining that mod f at x is nothing but f of x modulus. This is the definition. How we are defining modulus of a function? For the function value f of x, you are taking the modulus. So what is the idea here? If you take a function f, whatever may be the output result, we always consider the positive value of it. That is the actual interest under modulus. Clear? So if I say mod f at x and mod f at a means, if you consider f of x value, take its modulus. If you consider f of a value, take its modulus. That is the actual meaning of mod f at a and mod f at x. Okay? So here onwards, this result will follow. Thank you. So any more queries for this thing to anyone? Or is that clear? Fine. Now, at this context, one interesting thing is there. So here we have proved that if the function is continuous, its modulus is continuous. So what about the opposite case? It means that if mod f is continuous, is f continuous? That was the question tag here. So earlier you have proved one way, you are coming in the other way round. And let me say one thing, that one approach here is, whenever you want to prove a statement, if you want to say it is not correct, what is the thing we usually do? I have asked that, say P implies Q is my question. So if you want to prove that it is not correct, what you can do? Yes, assume correct, prove that you are going to get a contradiction, that is 100% perfect. What is the other way around? Contradiction, that is always correct. What is the other way around? Suppose if we assume it is correct, you are going to start a procedure, you are going to get a contradiction, so it is not correct, that you are going to say fine. So by starting with an assumption, you should go for a procedure, right? You don't know how to proceed, then what to do? So in such cases, we prove this by means of a counter example. Because if I say that it is a theorem, theorem means that whatever the conditions you are imposing in the hypothesis, if the hypothesis is valid, the claim is also valid in the theorem. So if you want to prove that this theorem doesn't hold good, you should check for a counter example, so that even though the hypothesis is satisfying, you are going to get a invalid claim. Similarly, I say that mod f is continuous, and if I want to prove that f is not continuous, I should find a counter example satisfying this condition, satisfying this condition. Fine. Is it clear? By means of a counter example, I am saying that mod f is continuous and f need not be continuous. F will be sometimes continuous, f will not be sometimes not continuous. It is a very simple example. Everyone will know that. There is no need to think a lot. Just define the function in a simple manner that you define the function like this. So what happens if you calculate the limit? Say limit x tends to 0 minus limit x tends to 0 plus. So what are the values? One limit value is 1, one limit value is minus 1. Accepted? So at the point 0, the function is not continuous. Agreed or not? All of you. Because both limits are existed, they are unequal, so it has jump discontinuity. Right. Now what happens if you calculate mod f? So for the images you are putting modulus. Therefore, mod f is equal to 1. It is nothing but a constant function. So whatever the value you take, 0, 1, 2, 3, minus 4, minus 2, minus 3, it is nothing but a constant function. So every constant function is continuous. So the example is, if you define f like this, mod f is nothing but a constant function, hence it is continuous, but the function is not continuous at the point 0. So this is the counter example, very simple one. Okay. Is that logic clear? Any more questions, please? You can ask if you have any other queries with you. Then I want to start an interesting concept here. Right, see. Is mod f continuous? Why? Because mod f is equal to 1, which is a constant function, it is always continuous. What is our claim? If mod f is continuous, is f continuous? What is the answer? Need not be. Why? Because this is the counter example. So take the example that define f like this. Define f from R to R by, for all non-negative values take it as 1, for all negative values take it as minus 1. Then the function is not continuous at the point 0. For the rest of the points it is continuous. So what happens if you draw the real line 0? Here it is continuous. Here it is continuous. But at 0 it is not continuous, because left limit, right limit both are unequal. Okay? Are you getting the idea? Right. So the function is not continuous at 0, but modulus of the function is continuous at every point, including 0 also, because it is a constant function. Is that clear now? Fine? Yes. So you can do that in the other way. If you have a small doubt that how the function is defined, as one of our friends, can you do it graphically? So this is the function we have defined. I choose the examples which are very easy to remember at the examination point of view, because the simple example you give, that is enough at the most. That also you can do. You can define like this. Can you say modulus of x is equal to mod x by x? Can you define like this? So if you calculate the left limit as well as the right limit, you are going to get the values as minus m1 and 1. To be remembered easy. So if you calculate the left limit, do you accept for this example? As per the mod x definition is considered, because mod x is defined as in this way defined. That's it. I am taking this kind of examples because whenever a point is asked to you, you should be immediately give the reply. There is no need to think more. The very simple examples are enough to give the counterpart. That's it. You can give very big examples, but those are not that much required, because you are just checking the validity of a hypothesis. Fine. So coming to the part, if you draw the graph, for x greater than or equal to 0, it is 1. So we are defining the graph like this. For x less than 0, it is minus 1. You are defining the graph like this. This is the graph of the function. So if you consider mod f, the graph will come like this. Whatever the part, it is always a constant function. Is that clear now with regard to the graphical approach? So there it is continuous, here it is discontinuous, as per the graphs are considered. Fine. So as one of our friends asked, can you do it graphically? For this counter example, you can give this graphical explanation. That will be somewhat good. Apart from calculating limit x tends to 0 minus and 0 plus, straight away you can do it by writing graphs. Okay. As per the counter example part is considered. Any more queries, please? Right. So here we are entering into one interesting concept. Sequence criterion, and other name is also there. We call it as Heinz theorem. Usually we remember with the word that sequence criterion. It is very best technique to decide the continuity of the function. So if you want to prove that the function is discontinuous at a particular point, I don't know any standard methodology or approach, what it may be, or I simply don't know. I am very poor. I don't know how to calculate the limit. So in this case, this methodology is very useful. So what happens? Let me give the concept first, then you will have an idea. Suppose f is a function defined from the set S to R the real numbers. Because we are dealing with real analysis, always we are talking about the real valued functions. Now what happens if you want to check the continuity of f at the point A? So it means that in the domain you can find a sequence which is tending to A. The theorem states that if you want to prove that the function is continuous at the point A, so in this domain you can consider any sequence, whatever the sequence you consider, you can consider that is converging to A. Then since for every part corresponding image will be here, so for A the image will be f of A. For this sequence an, you have corresponding image sequence here which will be f of an. Since it is converging to A, it must be converged to A. That was the actual thinking of the sequence criterion or Hein's theorem. It must be true for every sequence. So I have taken three sequences, an, bn and cn. All are converging to A. Then corresponding image sequences f of an must converge to f of A, f of bn must converge to f of b, and f of cn must converge to f of A. You can find what are the possible sequences which are converged into A. Then corresponding image sequence must converge to the corresponding image. That is the idea of sequence criterion. Is it clear? So if you are able to find at least one sequence such that xn converges to A and f of xn is not converging to f of A, then we say that it is not continuous. So it is very useful theorem for proving many problems, and some of the problems which are very good are given in UPSC based on this concept, sequence criterion. Okay? Is it clear? If the concept is clear, let us go with the problem straight away. Yeah, just to give a moment, I am going to take the necessary problem for you. Is it good in getting the idea of the concept? You need any elaboration over this? Thank you. I think this is one example given in the previous year papers. The function f is defined from R to R by f of x is equal to 1 minus 1 if x is rational, if x is irrational. This is the definition of the function given there. Take a note of it. And this type of function has a special name. We call it as Dirichlet function. This function is discovered by the mathematician Dirichlet, you can call. And what is our task here? F is discontinuous at every point belongs to R. So whatever the real number you take, at every real number f is discontinuous. That is actually you are going to prove. Now see, since real numbers are infinite in number, it is not possible to verify at each and every point it is going to be discontinuous, right? So this technique is very useful. So coming to the solution part, you consider the given function as it is defined. So since you are going to prove that f is discontinuous at every real number, so you can bifurcate the real numbers as q union q dash, the union of rationals as well as irrationals. You are going to prove that f is discontinuous at every rational number, f is discontinuous and at every irrational number, so that f becomes discontinuous at every real number. Okay? Is the logic clear? Right. So let us take that. Say a belongs to q is any real number, is any rational number. Or if you are bored with a, you can take another number. Just hold on a moment, I will fetch a chalk. Yeah. You take it as x. Now, what happens? What is my client? This I should prove by means of the sequence criterion. So, in the domain, I need to frame a sequence such that the sequence is converging to x, but the image sequence is not converging to f of x, so that I can able to prove that f is discontinuous at x by means of the sequence criterion. Okay? Is that clear? So if you have a little confusion, let us draw a picture that gives an idea. So in the domain R, I can consider any sequence which is converging to x. F of x will be here, corresponding image sequence will be here. So I should prove that f of x is not converging to f of x. I mean, f of x is not converging to f of x. That I should prove. So if you take any natural number between these, you can have so many rational numbers and irrational numbers. Accepted? For a little idea, let us take that x is equal to 3, a rational number. You give me n, any number please. You give me any number. 2. Right. So, if you consider x minus 1 by 2 and x plus 1 by 2. So, between this position, you can find so many rationals and irrationals, isn't it? Right. So, in this way, for every natural number between x minus 1 by n and x minus 1 by n and x plus 1 by n, you can find so many rationals as well as irrationals. So, since my intention is not to prove continuous, apart from taking a rational sequence, I can find a set of irrationals here. So, if you write the thing here means, if you consider xn here, so what does this mean? Xn is lying between these two. In other words, x minus 1 by n is less than xn, which is less than xn plus x plus 1 by n. So it is nothing but modulus of xn minus x is less than 1 by n. Could you agree? You can find a set of irrationals here belonging to this neighborhood. You can find so many. So if you have sequence of irrationals, you are selecting here means the sequence of irrationals are lying between these two values. So if you calculate the distance, it is less than 1 by n. In other words, you can simply correlate with modulus of Sn minus L is less than epsilon. This and this are somewhat similar. Agreed? So here the sequence is xn, limit is nothing but x, epsilon value is nothing but 1 by n. Fine? Yes or no? Right. So I got a sequence of irrationals in the domain which are converging to the point x which I have taken. Now I have identified a sequence in the domain. Now I am checking for the convergence in the codomain for the images. So let us go for this. So since x is a rational number, as per the definition is considered, whatever the rational number you take, if you calculate f of x, its value is 1. Since xn is a irrational number, I have taken a sequence of irrational numbers. For any irrational number, if you consider the image, its value is minus 1. So f of xn is equal to minus 1. So if you consider limit n tends to infinity f of xn, in other words, you are checking whether the image sequence has limit existed or not. If it is existed, is it equal to f of x or not, you are considering here. So this is equal to limit n tends to infinity minus 1, value is minus 1. So it is not equal to f of x because whose value is 1. So domain sequence is converging to x, but the image sequence is not converging to f of x. Therefore, as per the sequence criteria, f is discontinuous at x. Clear? So since x is taken as a rational number, f is discontinuous at every rational number. That was the conclusion. In the same way, without changing any step, with the same writing, we prove the second case. So what I am going to do, since I have proved that f is discontinuous at every rational number, the other part left with me is, I have to show that f is discontinuous at every irrational number. Here you have a doubt? Say? Yeah. Let me finish. You have taken that x is rational, xn is irrational. Am I correct? X is a rational number, xn is irrational number. Yes or no? X is any rational number, xn is sequence of irrationals. Right. Now, since x is rational, if you calculate f of x is 1 as per f definition, and f of xn is minus 1 because it is irrational. Now what happens? You are checking whether it is convergent or not. How to check the convergence? If you apply limit, you should get 1. So if you calculate limit n tends to infinity f of xn, it is limit n tends to infinity minus 1, value is minus 1. So it means that limit n tends to infinity f of xn is not equal to f of x because its value is 1, its value is minus 1. Both are unequal. So in the domain, I have identified one sequence xn which is converging to x such that the respective image sequence is not converging to the respective image. So by sequence criteria, the function is discontinuous. Okay? Is it clear now? Yes or no? So since you have taken that x is a rational number, from this part I have concluded that f is discontinuous at every rational number because x is rational. The other part is I have to prove that f is discontinuous at every irrational number. So the same steps will come. What I am going to do? Let x belongs to q dash is any irrational number. For n belongs to n, you take a sequence of rationals. So xn belongs to here. This is thing. This is the thing. So I have identified a sequence xn converging to x. So since x is irrational, f of x is equal to minus 1. Since xn is rational, f of xn is equal to plus 1. Limit n tends to infinity, f of xn is equal to plus 1, which is not equal to f of x. Therefore, f is discontinuous at every irrational number. So no change at all. Just you change rational as irrational, plus 1 as minus 1 in the proof, same thing will come. So earlier you have proved that f is discontinuous at every rational number. Here you proved that f is discontinuous at every irrational number. Hence, f is discontinuous at every real number. That is the conclusion of the problem. The explanation seems to be very tricky, but steps are very easy. You can see it on board. Nothing difficult is there. If you understand the concept of the sequence criterion. Do you agree? Why to bring it to that format? Means in the other way around you are asking, why should we prove sequence criterion or why should we consider sequence criterion? Yeah, because that form, if you want to ask in the domain, please understand the sequence criterion says that in the domain you can take any sequence which is converging to x. The concept is based on the convergence of the sequence. So you need to identify a sequence. What is the convergence of a sequence? Very simple. You are fixing a term number so that everyone is going to become equal. That's why you are taking the set of values which are going to become equal to x with a little gap of 1 by n. That's it. That is the whole idea. So if you are confusing about what is this mod xn minus x is less than 1 by n, you can think in other way around. Yes, for this step also you are going to prove that. If you want to prove that it is a continuous function, so you can say you are taking a rational sequence, you are taking an irrational sequence. Both are satisfying the same criteria. So xn converges to x. Xn may be rational, irrational. Whatever the thing you consider, f of xn is converging to f of x. If you have proved that it is continuous, that's all. Then also you can apply sequence criteria. The advantage of sequence criteria is you can find so many sequences in the domain which are converging to the point. You can consider any sequence. The corresponding image sequence must converge to the image. That is the idea. So if you are good enough to identify one sequence in the domain which is not satisfying this property, means you have done that, it is discontinuous. That is the whole idea. Why? Because if I have given that f from closely a b to r is a function, I have proved, I have asked that show that f is continuous at every point in that interval. So what is going to be done? You are going to prove the continuity at each and every point of that interval. Now think how much difficult it is. Right. Suppose in this interval, I have randomly picked a point C. And I asked you that at this point, f is not discontinuous. Sorry, f is discontinuous. Prove this. I have asked you. And I have given the function u also as f of x is equal to something. But the problem is, evaluation of the limit is very difficult for you. You don't know how to evaluate it. And it is very difficult to process this limit thing. So, at this position, this sequence criteria is useful. There is underlying logic here. Okay? So, I want to wind up our session here. So, in tomorrow's session, I will take more problems on sequence criteria, which is more important with regard to examination point of view. Then I will take the concept of uniform continuity in tomorrow's session. And we will discuss some interesting problems on this continuity concept also. So compared to infinite series, is this somewhat comfortable for you with regard to limits and continuity? Is the session somewhat interesting for you? Or are you getting a boredom? Right. So this part you are getting confused with regard to sequence criteria, right? Very simple. The very simple strategy is, if I take a rational number, you take irrational sequence. If you take an irrational number, take rational sequence. That's all. You take the opposite sequence. That is the whole idea. So by doing more and more problems on this concept, you love this concept of sequence criteria after doing the problems, which will be more interesting to you. So does the explanation hold good in getting the ideology? What we have done so far? Thank you. So please revise this concept of sequence criteria. Tomorrow we are going to do the same things on it. And this is most important with regard to exam point of view, because nearly 3 to 4 questions are asked earlier on sequence criteria. Thank you.